My name is Rotem. I'm from Weizmann Institute of Science. I'm working mainly on quantum cryptography, which is a very exciting field these days. And of course, for this, we need quantum communication. So I'm the first speaker. Let me also kind of explain what we mean by this. So communication, you have probably an idea of what it means. We have networks all over the world built for different types of communication, like the internet network, mobile phones, etc. And when we're now moving to the regime of quantum communication, we basically need infrastructure that can be used to transmit, sometimes also keep in memory, physical systems that carry quantum information. Okay, so we call this system qubits, quantum bits, like this series. Okay, so I don't know how many of you know what qubits are, so I'm not going to define things formally, but I'll tell you that there are three very important features that are being used within quantum communication, quantum information in general. So first is that in contrast to bits, what we use in today's networks and computers, that can be only 0 and 1, qubits can be in a superposition. They can in some sense be in both 0 and 1 at the same time. Another very important property is that they cannot be copied. The information that is stored inside the qubit cannot be copied without actually disturbing the qubit, without modifying the information. Okay, so this is something which makes it on the one hand very hard to work sometimes with quantum information, but also very useful for quantum cryptography. And the third property is that qubits can be entangled to one another. So here you can just try to think of two separated systems in space, in this network on the globe, and these systems are kind of somehow related to one another in a very special way, and they can share very special correlations. These features, they allow now, we can use them, we can now use this system in order to create new types of cryptography that are not impossible within the regime of classical cryptography with classical information. So let's even start with something much more basic. What is cryptography? So cryptography is about keeping secrets or sending some hidden information between different parties, communicating these secrets without third parties, bad parties that we call adversaries, gaining some information about the secrets. Okay. Now, in the context of quantum cryptography, you can imagine the following setup. So we have our good guys here in my slides are the rabbits. Okay, so these are the two rabbits. They want to communicate secretly. They want to share a secret without the adversary, without the bad guy, the fox here, learning any information. Now, using a quantum network, quantum communication, this rabbit can send a qubit from one side to the other. So it will send this physical system over to the quantum communication link. Then the fox can try to manipulate the system, can try to learn some information about what the rabbit wanted to send about the secret. But as I said, the information cannot be just copied without disturbing the system. So what happens is if the fox tries to gain some information about the rabbit secrets, then it changed the state. And now this qubit that was modified will be sent to the second rabbit, and the rabbits can use the fact that something changed, something happened because of the intervention of the fox, in order to understand that there is a malicious party trying to gain information about their secret and then abort. Okay, so this basic thing that I just showed you. This is one of the most important things that lead to what we call quantum key distribution. If you've heard of it, it's a very kind of famous task. With quantum key distribution, the rabbits can create keys that can then allow them to communicate completely secretly without the fox knowing anything. And this is something which is very unique, and it's impossible with classical communication. So the fact that the rabbits are sending these qubits, it's a fundamental thing that allows us to create these quantum key distribution protocols. Now, Another way of thinking about this situation is to think about a communication link that instead of sending qubits from one side to the other, we basically create entangled pairs of qubits, and then we send the qubits into the two directions. So here you can think of it as kind of as an infrastructure where we have the communication links, quantum communication links set up between the different rabbits, and in addition we have some entanglement shared between them, and then we can use it for whichever task that we want in the future. So let it be QKD, quantum key distribution, or anything else. So this is very cool. This is something this is what we want when we're talking about quantum communication. In my research, we take it even one step farther, and we're really doing something which is really unimaginable before you actually get to learn it. So we can even create a quantum key distribution protocol. We can prove that even if the rabbits do not trust the communication link and do not trust these systems that they're using, they don't know if there are qubits here. Even then, even if the fox was the one to create this communication link, the entire quantum network, they can produce a key in a way that the fox will never know the key and will never be able to gain information about the rabbit secret. Okay, so this is really something which is unimaginable. The rabbits, they do not need to trust anyone and can still create a key. So it sounds very strange. Why would we even want to do something like that? There are various reasons. So first, we can really take this paranoid point of view. We don't trust the manufacturer of the network, or we don't understand what's going on here. Okay, so we don't want to trust it when we create the keys and then use them for all of our communication. A second reason is the realistic reason, really, that when you actually create this network, it's a very complicated network, very complicated devices, and maybe you don't really know what's going on inside. Maybe there is some noise model that you cannot describe, you cannot anticipate, and you don't want your security proof to depend on a specific implementation. And then also, it's just really, really interesting. There are really fundamental aspects here. So I won't, again, get into the physics of what allows us to do it. I would say there are really fundamental physics aspects here, quantum physics, that are called non-local game, that basically tell us that some quantum systems can do things which are impossible to see with classical systems. And this is how we can kind of verify that the network that we are using is trustworthy. With this I end. Thank you very much.